Okay, so I will again repeat. There's going to be a lot of students that need to watch this because they are away on the Aths Carnival. So we're going to start with some astronomical measurements, okay? Now, as Michael from Vsauce said, in 1 degree, which is a rule of thumb, is if you hold your thumb out at arm's length, your thumb occupies 1 degree of angular size, okay? So basically that means you could stack 90 of your thumbs from the horizon to straight vertical. You could stack 180 of your thumbs on top of each other from east of the horizon to west horizon, okay? But then, if you were to... What does your thumb look like that? If you were to slice your thumb into 60 equal divisions, then each of those would be 1 arc minute. Okay, and as he said, 1 arc minute is getting to the limit of most people's vision. You can't really see angular sizes smaller than that. But we could keep going. Take one of those arc minutes and slice them into 60 again, and you get 1 arc second. So 1 degree is let's go the other way. 1 arc second is 1/60th of 1/60th. It's 1 over 3,600ths of a degree. And going backwards, 1 degree is made up of 3,600 arc seconds. Okay? Now, another example. Here's a poster. Comparisons of angular size. Now, as we said, the moon, it does fluctuate. It's around about 30 arc minutes, or half of a degree. Again, when it's near the horizon, there's a bit of a visual distortion and it appears larger. But to make this work, this chart will work when the distance that you view it from is 103 times the diameter. So can everyone stand at the back of the classroom, please? I'm going to put this sucker to be about 10 centimetres in diameter. Okay, all the way to the back. Please. So, this is 0.1 of a metre, and I'm assuming that you are all 10.3 metres away, so that you're 103 times further away than the diameter. Now hold out your thumb, and the moon, that's the approximate size of the moon in the sky, and it should occupy half of your thumb. There's a capital E at the top of the moon, and a person with 20/20 vision should be able to see that E, although it's a bit distorted and blurry because it's an image. Robert, stand at the front. Stand right there. So, also, due to the lack of resolution of our projector, there were also some items in that moon. Things like Venus and the International Space Station and Mars, they all have a size in the sky. And so, the size of them right now are proportionate to this. That's literally how big they are from our view. Okay. So back to your tables, please. Let's just zoom back in on that image, and in fact, we will see. I believe the sun. The sun. Look at that. The moon and the sun are almost the same size, and that, again, I think, is just a pure coincidence that we can get a perfect solar eclipse, because both the sun and the moon occupy the same of about half a degree in size. Okay? Now, I need you to appreciate how small an arc second is. So, here we go. I use the example that 1,000 metres away, there is an apartment building on the other side of Stirling Highway. Okay, in fact, there's two. There's one really close to Stirling Highway, the one with the painting of the squiggly circles on the side. Yes. And then there's one a couple of blocks behind, another high-rise apartment. That second high-rise apartment, halfway between Stirling Highway and the train line, that's going to be about 1,000 metres away. So next time you see it, hold out your thumb. What we're going to say is, what would an arc second look like, or if I subtended an arc second from the baseline, from the distance, what would the baseline be? So what length would x be if I set theta to be 1 arc second? Okay? And we can use our trigonometry. I can say that x is going to equal 1000 tan of our angle. Okay? And it comes out to be 0.0048 meters high. Or in other terms, 4.8 millimeters. So what that means is if we stared at somebody that's standing in that apartment, maybe on the balcony, and they held up their watch, then 1 arc second is going to be the height of their watch. And I'm talking not a big, huge, chunky Garmin. No, I'm talking your old Casios. Drawing an Apple Watch here. Your old Casios that have that little thin liquid crystal display. Okay? So if you remember those old school Casio watches, a very, very small screen. So that is an arc second of angular size if you're 1,000 meters away. Okay? Make sense? Cool. So just keep that in mind. Now, that's a method. That's pretty much the trigonometry there. It's very simple maths, okay? But now we're going to look at this simple maths using scientific notation, and we're also going to use different units of length. So instead of using meters and centimeters, we're going to use astronomical measures, okay? Which gets a little bit tricky. However, next example. Are we still... how did I bring up that? I just want to make sure we're still screen capturing. Yep, cool. Oh, thank you. That just ruined the lesson. Oh, there's Michael. There's every other screen that I want except for parallax. Okay, hold out your thumb again. Okay, cool. Now, cover my head with your thumb. All right? Now, look at me. Cover my head. Block one eye. Close one eye. And then block my head with your thumb. Now, I'm going to use Sean. Now, without moving your thumb, change your eyes. My thumb appeared to move relative to Sean's head. And you should see the same. Your thumb should appear to move relative to my head. My head is really, really far away, so it's not going to move. There will be no parallax, okay? Another thing you can do, it doesn't work, use your thumb again, and we can use our rule of thumb. It looks like my thumb has shifted about 3 thumbs. And so when viewed from a different eye, my thumb appeared to shift by about 3 degrees. So I just used a couple of rules of thumb there to figure out some parallax. So, here's the cool thing. Suppose I'm limited to a ruler of 30 centimetres and I don't know the length, I don't know how far away the thumb is from my eyeballs, but I know the distance between my 2 eyes and I can measure that angle to about 3 degrees. So I could use my friend trigonometry and the effect of parallax. Here are my eyeballs, okay? There's my nose. And we know that my base length is known. Okay, the distance between the 2 pupils. I'm going to go, here is... now, for the sake of this example, let's put my thumb there. Okay, and I'm going to measure... And there's Sean. Okay, the distant background. And then when I view my thumb, okay, Sean appears to have shifted. So, it's just triangles and measurements of angles, okay? So that's the whole thing. If I don't know how far my thumb is because maybe I don't have a ruler long enough, then I can use trigonometry. You know, half the baseline, I've got my x length, all I need to do is measure an angle, okay? Now, we can do this. So over here, let's just say this is a object in the sky and we have it against distant background. Now, it turns out, fortunately for us, lots of the stars in the sky are really, 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 really far away. So a nearby star is like my thumb relative to Sean Tanner, or the back of the classroom, okay? So a thumb that's close can be measured using this method because the back of the room doesn't really appear to change due to parallax, okay? Now, here is our angle theta, and if I'm over here, and I take my measurement, well, I'm going to measure where that object is against the distant background. So my thumb was right next to Sean Tanner, okay? Now, it turns out we can take measurements from different positions because we are on this big ball of rock orbiting a big ball of gas. I don't have any orange pens, so here is the sun. And in 6 months' time, I could take my measurement again, and this object, again, from the background stars, has appeared to shift. Now, I did my measurement, a tenth of a second later, I was able to measure that, oh my God, Sean moved. But if I was to slowly move my eyeball along over a period of 6 months, my thumb would slowly appear to drift in the sky and Sean stays stationary. Okay? So, for example, we could take our measurements in January, get very, very precise measurements of the angle, and then maybe in July, 6 months later, okay? Now, the great thing is, we know this distance. This distance is known as 1 astronomical unit. I'll write that, astronomical unit. And in fact, in your data sheet, it tells us that astronomical unit. In our data sheet, it says that the mean Earth-Sun distance is 1.50 times 10 to the 11 meters, or 150 million kilometers. Okay? So you might need to get that value when you're doing Kepler's law, if we're ever looking at, the motion of the Earth around the Sun. That's the mean distance that we are from it. Okay? Now, so here's what astronomers have been able to do. Since we are travelling 300 million kilometres apart in 6 months, some stars are going to appear to shift. And so we can measure the apparent shift, we can measure the angle theta, and knowing the base length is the diameter or radius of the Earth, it enables us to calculate the distance d. How far is that object from us? Now, this diagram is not really to scale, right? Because we're talking about tiny, tiny angles. In fact, the angle is getting so small that the hypotenuse is going to approach the adjacent. It's like one of those limit questions, yeah? It's limit as theta approaches 0, h approaches a, or something like that. So really, it's going to be negligible whether we're measuring the hypotenuse or the adjacent side length. Now, I need you to think of that method of parallax and remember the idea that 1 arc second subtended in the sky from 1,000 meters away is going to clear or move a base height of 5 millimeters. Just remember that, the wristwatch of the bloke sitting in the apartment 1,000 meters away. So, this is how I explain a parsec. Now, over the page. A parsec is another measurement of distance. It is how far away you need to be such that the subtended angle of 1 arc second is the distance of the Earth from the Sun. So I said I need to move away from the bloke's wristwatch 1,000 meters so that the bottom of his watch to the top of his watch subtends 1 arc second. If I went further, how far would I need to be such that the area subtended from bottom to top was the actual mean Earth-Sun distance? It's really, really far, okay? So, but this is what we do. Look, here's a close star. We measure the angle here in June, and it appears to be near these guys over here, so in June there. And then it appears to shift. It seems to wander, okay? Well, again, I'm not going to, just, I don't know. Louis, move your head backwards and forwards. Right? Does Brownie seem to be wandering between you and me? Yes. Well, it's not that he's moving, it's that I'm moving. That's the whole thing with parallax. Just sort of Move your head backwards and forwards slowly, and you might notice that me, Mr. Murray, appears to move relative to the background. Yes? But I'm not moving. You're moving. Right? You're orbiting a sun. You're doing this. You're going, oh wow, Brownie seems to be spinning around in his seat. No, he's not. I'm just moving, and so I can take measurements at different times using trigonometry. So, here is our diagram. So basically, how far must we be away such that the area subtended produces a base of 1 astronomical unit? So let's just do some trigonometry, please. Let's figure it out over here. I'm going to just keep things in astronomical units. So we'll go 1 parsec. Oh, let's try that again. 1 parsec equals 1 AU divided by the tan of 1 arc second. Now, that angle's really, really small. The tan of that angle is going to be even smaller. And when we divide by a really, really small number, we get a huge number. 206,265 astronomical units. Which, if you notice, in the wiki page, we have there. Okay. Oh, thank you for doing that. We have there, okay? Oh, by the way, let's just scribble out this. We don't really care about United States of America with their silly imperial units. We don't have to worry about that. Okay. Now, I told you our conversion. We said 1 AU is 1.5 times 10 to the 11 meters. So let's convert this to SI units. And so in SI units, in meters, it's 3.09 times 10 to the 16 meters per parsec. And you'll notice there we have in the wiki page, we've got the SI units of a parsec. 3.09, 10 to the 16. Okay, now, side mission here. We might want to get it in light years because those are the 2 astronomical units. We've got the light year and the parsec. And the astronomical unit. There's 3 of them, I should have said. Astronomical unit is good for, solar system distances. Light years and parsecs are good for really, really far away things. So, 1 light year, and I'm sure you all remember, but between pre-primary to now, a common misconception is that it's a unit of time. No, it's how far light travels in a year. It's a unit of distance. It's the speed of light multiplied by the time in a year. So let's just do a quick little how many meters is that? 3 by 10 to the 8. We'll use 365.25 times 24 times 60 times 60. Now, remember there's a leap year. Yeah? Every 4 years we have to add a day. So in a year we're going to have a quarter there. Now, a student, there was a question a few years prior that required the seconds in a year. And if you use 365, you're not penalised because to 3 sig fig it's the same. But some students use the 0.25. That's fine. Calculator spits out 9.47 times 10 to the 15 meters per light year. Okay? Now, here's where my friend dimensional analysis comes in, because we have meters per parsec and we have meters per light year, but we want light years for every parsec. So let's just quickly look at dimensional analysis. We've got meters per parsec, and if I divided by meters per light year, then we would get a cancely, we would get an inverse of an inverse, and we would get light years per parsec. Or how many light years for every parsec of distance. So I'm going to use that one. So let's take our 3.09 times 10 to the 16 meters per parsec and divide it by 9.47 10 to the 15 meters per light year. And the cancelies, we get 3.26. Light years for every parsec. And that is the last conversion on our wiki page of parsec units. Okay? So, let's put that into context. Let's say that I am a photon of light and I start at the sun. I am ejected from the sun and I travel off in a straight line at the speed of light, away from the solar system, out of the solar system. And in 3.26 years, I look back at the sun and the earth, and they're 1 arcsecond apart in the sky. Okay? Again, 1,000 meters, bloke's wristwatch. The particle of light is now 3.26 light years away, Earth and Sun. So again, these are so large values that our little primitive monkey brains, we can't fathom 10 to the 15 years. All right? When we evolved or were created, we were sort of given a 10 to the 3, 10 to the negative 3. You can kind of see something a few thousand meters away. And you can kind of see something 1,000th of a meter small. But a nanometer, our senses can't correspond or can't, comprehend. And if I told you that Sydney is 3 million meters away, 4 million meters away, oh, yeah, that's really far. Now, our brains can't fathom how far away Sydney is, let alone 9 to the 15 meters. So, this is all just trig. Okay, Year 9s could be doing this with just nice numbers, but obviously we're using new terms that you're not familiar with, which is why, if we have a look at the data sheet, I want to tell you that they have given you, oh, there it is there. They've given you a few conversions. These bottom two are new. They have been added to the data sheet. Okay, just like the standard model poster was changed. They got rid of spin and they added baryon number and lepton number to the standard model poster in the data sheet. These bottom two have been given to you. But just be careful, they've been given in kilometres. But there's our 3.26, and it's a mega parsec. Because it turns out that even a parsec, as big a distance as it is not big enough because things are further away. We have to talk about millions of parsecs. So this is 3.26 million light years. Turns out there are galaxies that are millions of light years away. More on that later on this lesson and next week. So, back to your book, please. Let's turn the page. Recently, here's an example. Proxima Centauri that's our closest star. It's 4.24 light years away. But it appears in the night sky with a very, very small angular size, the star itself. Okay, so there's our diagram. Remember though, unfortunately, seconds and minutes are base 60 and we want decimals, we want base 100. So we're going to have to go, here's our angle theta equals 2 milli arc seconds. I'll highlight this again as I say it. 2, we've got that there, 2 milli, right, arc second. Yeah, cool. So dividing by 3,600 converts your arc seconds into degrees. So again, some very, very quick trig. Our base length x is going to be 4.24 light years times by the tan of the angle, 2 milli light years. Now, I've left that unit in here because we're going to get an answer. Yeah, if our dimension is in light years, then our answer will also be in light years. So we get 4.11 10 to the negative 8 light years. Well, here's the thing. We want to convert it to SI units. Now, I could have converted up here. I could have converted him to meters, but let's just do it here. We're going to go multiply by 9.47 times 10 to the 15 meters per light year. Cancely, and it'll convert it into meters for us. 3.89 by 10 to the 8 meters. And that sounds okay for a star. That's about 100 times the size of our planet. About. I might have made these values up, so don't go Google searching Proxima Centauri and finding its angular size, but that's just an example there. Okay. Again, I borrowed this paragraph. I don't know what effect they're talking about. Probably the fact that we are underneath the Earth's atmosphere. We're stuck beneath a 40,000 metre blanket of gas, and that can distort the light. Light that comes in from distant stars can be refracted and bent and scattered and things like that. So to get rid of this distortion of information, thank you, let's put our telescope in orbit around the Earth, and that way there's no distortion of our information. So, the Hipparcos satellite was sent up, and it had a precision of 0.97 milliarc seconds. But then, recently, ESA, the European Space Agency, launched Gaia, which had a precision, it measures 1 billion stellar objects to within 20 microarc seconds, plus or minus 10%. So, let's figure out how far away this Gaia telescope could reach. Okay. Now, unfortunately, I didn't give you the diagram, but that's okay. Here we go. We're trying to solve for x. Here is our sun. Here is our Earth. And around it spins a satellite. And the satellite is going to be taking very, very precise measurements of our distant object. Still against a distant background. Okay? So that's why you still have to measure it. Now, remember, our little Gaia is taking incredibly precise measurements of angle, and then 6 months later, spinning around the same lump of rock, our Gaia is then going to take, didn't mean to do that, is then going to take, again, very, very precise measurements of these angles. Now, again, this is not to scale. These are very, very far away objects. If it was a scale diagram, we wouldn't be able to draw it, but these angles would be very, very tiny, okay? I'm trying to think of an example. The further your thumb gets away, the further it appears to wobble in the sky, the smaller the angle that it will appear to change. So, we're going to set the minimum angle, theta, here to be 20 micro arc seconds. That should be a 3,600. Okay, so there's our theta there. We're nearly there, we're nearly there, we're nearly there. All right, let's solve for x. Now this, we're going the other way. Here's our base, which was 1 AU. So now we'll say, I don't know, tan theta equals opposite over x, x equals opposite over tan theta. 1.5 times 10 to the negative 11 over tan of 20 micro arc seconds. .55 times 10 to the power of 21 meters away. Good Lord. Let's get it to those other astronomical units. So then let's divide by 9.47 times 10 to the 15 meters per light year. Cancel-y, inverse of an inverse. And we get in light years 1.64 times 10 to the 5 light years, 164,000 light years. And then lastly, let's use that 3.26. And that was light years per parsec. Again, dividing, so it's going to be cancely, inverse of an inverse. And we get 50,300 parsecs. So currently, that is the limit. Okay? So even most recent uses of parallax. By the way, it turns out there are other ways of measuring the distances to far away stars, but the parallax method of measuring the apparent movement of a star due to us observing from different spaces in space allows us to measure things as of 2013. It can be doing 164,000 light years away. So the Gaia satellite, 1 billion stellar objects. So have a think. It takes a measurement of a star. Let's say Sean. There he is. Take his measurement. Where is he? Got him. 6 months later, that telescope is going to come back to Sean. Where's Sean now? Ah, there he is. Got him. Take the measurement. Beautiful. But it's doing that for 100 billion things. So it's, all right, where's Sean? Where's Ben? Where's Callum? Where's Lockie? Where's Brownie? Where's Willow? All right, boom, 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 as it's moving around. Have a look here. This is a scale diagram of our galaxy. I cannot talk and write at the same time. This is a diagram of our Milky Way. And you will see that it's only 100,000 light years wide. And so that Gaia satellite is only able to measure the stars in our own galaxy. Okay? And it wasn't until the 1990s that we realized that that is not the only galaxy. Okay? Before, I don't want to Hubble, redshift, whiteshift. Wait, no, sorry, Hubble. Whenever Hubble was around, it's in your booklets. Hubble figured out some stuff, but up until that point, we didn't realise that we were just in one tiny little galaxy and there's many other galaxies. We just thought it was the universe. Back to what I was getting at. Most galaxies are very similar, and they have, on average, 100 billion stars. Okay, in each galaxy. So in this diagram, there's about 100 billion stars, and ours is one of them, about here. Next, you might have heard the romantic story of you go out at night and you gaze up at the night sky, and you're not looking at the stars as they are now. Have you heard this story? You're looking at them as they were how long ago? Huh? I do.
100,000 years.
Huh?
100,000 years.
No, that's too much. Tens of thousands of years ago. So here's the thing. Most objects in the night sky are only about 10,000 light years away from us. Beyond that, we need telescopes. Now, there's a couple of nebula. There are a couple of galaxies that we can see with a telescope nearby to us and bright, but most things that we see are in our own galaxy. With our eyes, we can only really see the nearest stars that are 10,000 light years away from us. But that's still quite a romantic story. Light leaves a star, and then the Egyptians, and then Hitler, and then Christchurch Grammar School. Wait, hang on, no, Christchurch Grammar School came first, then Hitler, then us. 10,000 years, that's still a long time. Okay? And think about it. This, Charlie Hewitt, this little photon of light left its star and it travelled through the empty vacuum of space for 10,000 years for it to enter our atmosphere and then fly straight into the back of your retina. Dunk! And you go, oh look, a star. And then you just keep walking. Yeah? Think of that photon's life for it to be wasted by striking the back of your eyeball when it could have just hit the ground next to you. Been more useful. Okay, crazy. Really makes you think. So, that's about me done. For those of you that are watching at home, I'm about to play the second video. We watched How Big Can a Person Get? Now we're going to watch the Monty Python's Galaxy song, which I'm sure you will all enjoy.